Here we go. Here's 6.3, applications of normal distributions. So the biggest concept is here is we just talked about the standard normal, and now we're going to talk about how we can use it for all normal distributions. Basically learn that z-scores are what converts all of these things. So converting from a non-standard to a standard normal distribution. So just having a normal distribution, it's non-standard though, right? So that means the mean isn't equal to 0 and the standard deviation isn't equal to 1. We can use basically z-scores to make a normal distribution fit the standard normal distribution. Hence, we can use that table A-2 to help us do these problems. What's so cool about it is the non-standard normal has a mean mu, which might be some value, and then we're going to convert it to a standard normal where basically the mean is 0, right? The standard deviation is 1. But we use the z-score formula to do that. And then we can use that table for any of those things. And that's what we're going to do here in these examples. So when finding areas when a non-standard normal distribution, use these procedures. Sketch a normal curve. Sketch, sketch, sketch. I can't stress that enough. If you guys do this, you sketch it, you label it, you'll be amazed at how much more clear it makes sense to you and how faster I think you'll get it. Not sketching and just trying to answer questions without sketches, leave you a little bit questioning how you do this. For each relevant value x that is a boundary for the shaded region, use the formula 6 to convert the value to the equivalent z-score. And you can use technology to find these too, but you should really feel familiar with the table. Here's an example. So let's apply those steps. So here's example 1. We have why our doorway is basically a height of 6 foot 8 inches. In other words, 80 inches. It's because we find that majority of the population fits inside that. So given the following information, given that the heights of men are normally distributed with a mean of 69 inches and a standard deviation of 2.8 inches, find the percentage of men who can fit through the standard doorway without bending or bumping their head. Is the percentage high enough to continue using 80 inches as a standard height? Will a doorway height of 80 inches be sufficient in the future years? Okay, if we want to go and use this, right, non-standard and make it a standard normal, we need a mu and a sigma. Hopefully you caught on that basically knowing the mean from the distributed men population, 69 inches, and the standard deviation was 2.8 inches, okay? So if we go back here, we know sigma and mu. What's x? X is the value that we're testing, which is this 80 inches. So 80 is what we put in there. So we'd have 80 minus 69 divided by 2.8. Notice I put in the sample statistics. You could have mu there and you could have sigma, just a small notational thing. Just want to make sure you know that both will work, okay? Anyways, you end up with a z-score of 3.93. We are not done. That just tells us basically the z-score. We need to figure out the area or basically the probability or the percentage of people who will fit under the door. And it looks like it's almost like 100%. It's 0.999999%. In fact, if you look at your table, you'll see 3.50 and up is 0.9999. Basically means that, you know, it's very, 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 very small portion of the population that is actually taller than 80 inches, and that will not fit through the doorway. All right, here's another example. Birth weights in the United States are normally distributed with a mean of 3,420 grams. Right there, you know mu. Boom, 3,420 grams, that's mean. Standard deviation of 495, that's sigma, or you can think of it as S. The Newport General Hospital requires special treatment for babies that are less than 2,450 grams, unusually light in their weight, or more than 4,390 grams, unusually heavy babies. What is the percentage of babies who do not require special treatment because they have birth weights between 2,450 and 4,390 grams? Under these conditions, do many babies require special treatment? So if we go through, this is basically, we're trying to calculate the probability that a baby has a weight between these two. Again, you'd find the upper bound is 4,390, subtract the mean, and then divide by the 495. That'll give you a z-score. Then you find that area, and then you'll subtract the lower bound area from that upper bound. So again, you take 2,450 as your x value, minus it from 3,420, and then divide by 495, you'll get a z-score. And you get an area, and you take the two areas and subtract them, and that's how we get 0.95. In other words, 95% of babies do not require special treatment based on this. So again, you might be wondering, why haven't you sketched this out? Check out my other examples. I do have these sketched out. I just wanted to walk through more the answers and talk about it. Again, helpful hints. This is the same slide you've seen before, but it's just a reminder. It's very helpful. Now, let's suppose instead we want to do some algebra. Previous. Other way. Algebra. And we want to find an x value that is a cutoff for this. Well, we can times sigma over here and then add mu over here. So we have mu plus sigma times z is equal to x. That's exactly what we're going to do here. We want to find a value from a known area using the table. So in other words, in this case now, we're going to find the cutoff bounds. And I'll give you an example here in a second. All right, again, what does it say here? Refer to the sketch of the curve to verify. What does it say up here? Sketch. Okay? You got to sketch these things. It would be really helpful. So when designing an environment, one common criteria is to use a design that accommodates 95% of the population. How high should doorways be if 95% of men will fit through without bending or bumping their heads? That is, finding the 95th percentile of heights of men. Heights of men are normally distributed with a mean of 69 inches and a standard deviation of 2.8. Let's write down the information we need. Well, hopefully you'll find out that you'll need 73.60 inches for 95% of the population to fit through it. Okay, that's our mean, that's our standard deviation. If we go this way, we know mu, we know sigma, we need to figure out what z is, which I think if you go and look, you'll find that should be 1.645, and then you do the computations here, and you'll get that 73.606 inches. Here's another one, and this is a really good one. It's again the General Hospital, but instead now, after some recommendations, they've decided that the lowest 3% of babies, in other words, babies with the lowest 3% weight, need special treatment, and the highest 1% need special treatment. But we need to know what those weights are. Well, we have a mean, we have a standard deviation, and what we need to do now is take this percentage, like the lowest 3%, we need to find that z-score that corresponds to it, so we can do that formula. So here, take your table out, find 3%, lowest 3%. It's going to be in the negative side of the distribution, so you should sketch that out, and you'll have basically that area of 3% in the bottom half of the distribution. And if you're looking at your table, you should see in the body of it that basically 0.0307, right, our area code here in Wyoming, and 0.0301, and it lies between negative 1.88 for a z-score. So that's going to be what we're going to plug in for this z part right here. Okay, so that's our lowest. And then we do that calculation out, you should get 2,489.4 grams. Okay, that'll be the lowest 3%. If we want to calculate the highest 1%, we need to figure out where 0.999, did I say too many nines? 0.99 is on our body of our table for the positive side. So you look at the body again, right? The body or the area, it's what you would have highlighted the box around. And I think you're going to see it's probably about 2.33 for the z-score. So find z 2.3, then move over to the right. You'll see the column of 0.03, and you'll see 0.9901. That's the value we're going to use. Yes, it's not exactly 0.99, but it's pretty dead on. It's 0.9901. So we'll times that, 2.33 times the standard deviation of 495, and then we add it to the mean, and then that's how we get the 4,573.5 if we round one decimal place. Kind of a summary of what we want to do. This is a really good flow chart. If you're ever like trying to solve these problems and you're really confused, you need to figure out, am I finding a probability or am I finding a value of X? Depending on which one you're trying to do will determine which one you're going to, which like path you'll take, right? If you want to find a probability, are you going to use technology? If you use technology, boom, it's really simple. If you're going to use the table, which I recommend you do so that way you really understand it, because we will basically get test statistics and p-values later generated from technology. But if you don't understand right now what this value is, when you start getting those, it'll be very confusing. So I would recommend you do it by hand for the first couple times, use technology to double check. But yes, we'd find a probability by converting our standard normal distribution by finding the z, right? So we find the z-score, we look it up, find the cumulative area to the left, if that's what we're trying to find, or if we're trying to find the area to the right, we got to do 1 minus it. If we want to find a value of x, identify the cumulative area to the left, right? Whatever we're trying to find, or the shaded area. And then are using technology. Again, I would recommend that you use the table, make sure you get comfortable with it, and then use technology. And that's all 6-3. So let me know if you have questions. It's really good. And if you still have questions, like, I don't understand how you did some of those calculations, watch some of the other videos I have, because I actually have just a handwritten part of the problems with no slides on them, okay? So just doing the problems.